Hey physics friends, and welcome to 17.3, which I've entitled Ray Tracing. Today we're going to learn why we see other people, why do we see ourselves off of a mirror, and can you predict what an image off of a mirror will look like? I kind of want to get us started with this really interesting video that I saw a couple weeks ago that I thought was pretty interesting. It's a professor, he's got a ball, and it's swinging back and forth in front of what's a concave mirror. And what's interesting is you watch this thing go back and forth, you'll see that the pink is on the top and the blue is on the bottom. But when it's all the way forward like this, it's inverted. The blue is on the top and the pink is on the bottom. And when it swings all the way back here, now it's right side up. So it oscillates between being right side up and upside down as it swings in front of this mirror. And why is that? We'll talk about that. That's the goal today, is to answer this question. And why we see ourselves off of a mirror. First of all, why do we see other people? Each of my head, my arms, and my feet, they're all reflecting light in all directions. And some of that light from each of my extremities goes into my eyes. So what ends up happening, and this is what we call, it's called a camera obscura or a pinhole camera. Inside of a pinhole camera, you've got light from the top of the tree, and that light goes through the hole, and our eyes have a hole in the front of it. They're called the pupil. And then it gets projected on the back of our eye, which we call the cornea. The retina. So, our eye is kind of a sphere, and there's a hole in the front of our eye. And on the back of our eye is a screen, much like this. And so you'd get this like tree projected on the back, and there's a bunch of cells that then take that to your brain, and your brain makes it right side up. Like the image from the world around you is being projected on the back of your eyeball in this manner. And I want to show you a quick video where this person makes a cardboard camera obscura at home. So they just take a piece of cardboard, they're cutting a hole in it, and they're just grab a lens, and on the back side this is tracing paper. So there are two pieces that kind of like sleeve together like this, and on the front side is their lens again. And so then you take it to a really bright object, and then you can look through this and you adjust the focal length, pushing that forward or backwards, and you get an upside down image projected on that tracing paper. And what you can do too, you can put different colored or different size holes to represent letting different size amounts of light in if it's too bright. And this is what our pupil's doing when it's getting smaller or getting larger. So why do we see people? Light is entering into both eyes, and because we have two eyes, we can tell how far away things are. We call that stereoscopic vision. If you only have one eye, you should try to shoot a basketball with one eye one time. You can't tell how far. You lose your depth perception when you only have one sensor. So with two sensors, we can kind of tell. I mean, you can use your finger, and you can see your eyes pointed in to see something, and then they're far away, your eyes point out. And because of that, we can tell how far away things are. Why do we see ourselves in a mirror? The exact same idea is that now, why we see ourselves in the mirror is exactly the same way others see ourselves. The top of my head is giving off light, and that light is being reflected off the mirror. But if you were to trace where those rays are coming back to, it seems as though there's a person's head from where that is coming from, and a person's foot from where my foot's coming to, and so on and so forth, kind of making up my entire body. Like the reason I see a person is it seems as though light rays are coming from that spot. Well, first of all, we're going to do some definitions. We're going to be working with both concave and convex mirrors here. And a concave mirror is a mirror shaped like the inside of a sphere. It's curved, it's caved in. Caved in. The principal axis is a line through the center of the mirror. Center of curvature is exactly how it sounds. Is if you were to take a compass and you were to put the pointy part of the compass right on the center, and you were to draw the line, this curved mirror would be centered at the center of curvature. The physical center of the curved mirror. The focal point is where all rays parallel principal axis converge after reflecting off the mirror. And you can see I have a whole bunch of rays here. This ray comes in and it bounces and hits the focal point. This ray right here bounces into the focal point. The focal point is where all reflected, as long as it's parallel to the principal axis, they'll reflect through this one point. The principal plane is a line perpendicular to the principal axis through the mirror. So the principal plane is right here. There's an imaginary line we call the principal plane. And this line right here we call the principal axis, the center, and the focal point. And this is a concave mirror. So just a few terms that we need to get in the books here. Next, there's a couple different types of concave mirrors. You can have a spherical concave mirror, or you can have a parabolic concave mirror, and we have something called spherical aberration, where truly the reflected rays don't all go through the focal point. If it's spherical, it's called spherical aberration. You get kind of a blurry image. Maybe some of you with glasses, if you look at the edges of your glasses, you'll get like blue and yellow fringes along that's called chromatic aberration. It's a defect that colors aren't all refracting at the same angle, and this is all the lines aren't reflecting, and this is called spherical aberration. So if you have a parabolic mirror, it fixes that problem where they all go through, but there is a defect if it's a sphere. So to truly make this work well, you need a parabola to do that. Convex mirrors. Convex mirrors, they have a negative focal length, what's known as a virtual focal length, because the rays on a convex mirror, the rays come in, they hit the mirror and they bounce this way. This ray hits the mirror and it bounces this way. This ray bounces that way. So they're all bouncing away from something, and if you trace those backwards, there's your focal length. So this is a negative focal length. It's a virtual. This is the first foray that you're going to see where something is reflecting and it's on the other side of a mirror. Don't get in the habit of thinking, oh, something's on the other side of the mirror, that makes it negative. That will work for you in this chapter. In next chapter, when we talk about lenses, it doesn't work, and then it just gets all crazy in your brain. Think of it this way. If you have to trace something backwards, see, like I had to trace this ray backwards. Oh, I had to trace this ray backwards. I had to trace these rays backwards to find something that makes it virtual and that makes it negative. The next lesson, you're going to be putting math to this, so the fact that it's negative is important. When we do the math, the focal length is a negative number because we had to trace this ray backwards. Curved mirrors. We get all sorts of crazy images. You saw before. These are like in a fun house. So if you're in a spoon, if you look in a really shiny spoon, you get a convex and a concave. Why do you get crazy images when looking in a curved mirror? And we're going to talk about how to actually figure out what an image looks like. This is called the graphical method for finding the image of a concave mirror. Sometimes is referred to as ray tracing. We're going to do some ray tracing to figure out what the image looks like. So step number one when you are doing ray tracing is you have to draw the principal axis and the principal plane. So there's step one. Step one's been done for you in all of these. A lot of times the biggest mistake I see people doing is they don't draw the principal plane if it's not given to you. Step 2, draw ray 1 from the top of the parallel. I'm just going to do it and show you what I mean. So ray 1, I'm going to make it a ray. We'll make it kind of skinny. So ray 1 is going to come off. It's going to go through the mirror, and you got to go all the way to the principal plane. The ray is going to bounce off the mirror and go through the focal point like this. So here's my ray. That's how it's going to reflect off that mirror. Go all the way to the principal plane and then reflect it through the center. Ray 2, what you're going to do is you're going to draw a ray to the middle. I'm on step 4 now. Draw ray 2 from the top of the object to the intersection. Now, using the law of reflection, I'm going to take a ruler here, and I'm going to take this ruler, and I'm going to measure. This is 2 centimeters tall. I don't know if you can see that, but this is 2 centimeters. So if I measure up 2 centimeters, I'm going to go down 2 centimeters. I'm going to put a dot right there. So I don't need a ruler. I could use a piece of paper too to mark that distance. And then just bring this distance down here and put a dot. My reflected ray is going to go off the principal axis, and it's going to go through that dot like this. Remember, I just measured the distance from there to there, and I copied that distance down below right here, and I could put my dot there. Okay, my reflected rays. The reflected ray is this one and this one. Those are the reflected rays. This is the incident. Let's get this out of here. The reflected rays will cross, be parallel, or diverge. Where they cross is where the top of the image is formed. So right here, they are crossing. That's the top of my image. So my image is going to be smaller, inverted, and real. Real means that the rays actually cross. You'll see here in a bit where they don't actually cross. Let's do that again. So we'll do it for the next. So now we'll stand on the center of curvature, and watch what happens when you stand on the center of curvature. Ray number 1 goes in, and it bounces off the focal length like that. I'm going to, again, measure how tall my object is. I'm going to come down below it, make a dot. My dot looks to be about right there. And then I do ray 2. Ray 2 goes to the middle, and then it reflects off through my dot. And these rays cross. Where they cross, that's where the top of my image is. So this image is actually right exactly where the object is. It's the same size. I'm going to put a letter I for image here. An I for image. The image is the same size, it's inverted, and it's real. It's real because the rays actually cross. We'll see in a bit where they don't actually cross. Here's another one. What if you're in between the center of curvature and the focal length? Ray 1 comes in parallel to the principal axis, bounces off through the focal point. Ray 2 goes to the middle, and remember, we're going to measure how tall this is, go down below it, we're going to put a little dot right there, and then we're going to reflect through that dot right there. The reflected ray, here's reflected ray, where the reflected rays cross, that is where the top of my image is located. So here in this case, my image is larger, inverted, but still real. And you'll see, the first one was smaller, the second one was the same size, and then my one that I just did right here, now you have a larger image. And you saw that happening. Well, I'll put all these together to take it back to that very first video that we saw of that guy swinging that ball. Now, what happens if you stand on the center of curvature? Something really special happens when you stand on the center of curvature. Let's figure it out. Ray 1 comes in, and it bounces through the focal point. Ray 2 goes to the middle, and remember, we have to measure our object, come down below it, put a dot, and then we will reflect through that dot. I should have done a better job with my dot. Oops. I'm sorry. My dot should be right here below it. And you'll notice that these rays are parallel. So there's no image in this case. This is no image. It's not larger or smaller. It's not inverted or real. Inverted or upside down. There's no image. These rays don't cross. When you're on the focal point, you have no image when you're dealing with a concave mirror. What if you're in front of the focal point? As we have right here. Ray 1 comes in to the principal plane, bounces through the focal point. Ray 2, we're going to measure our object. Sorry. Put a dot below it. Ray 2 is going to hit the center and bounce off. Now, these are diverging. Remember at the beginning I told you that you could have, they're either going to cross, be parallel, and we've seen these two so far. They've crossed and they're parallel. Now they are diverging. Here's where we're going to have what's called a virtual image. Here, these are diverging, so what I'm going to do is I'm going to trace them backwards with my ruler. And this seems right here is where the top of the image is located. So this image right here, this image is upright, larger, and virtual. It's virtual because we had to trace our lines backwards. If you ever trace anything backwards, that makes the image virtual. To our eyes, we cannot tell the difference between a real image and a virtual image. They look the same, but a virtual image cannot be projected onto a screen. Only a real image can. And so what you're seeing here, if you can put all these things together, when you're on this side of the center, you're always upside down, upside down, upside down, upside down. But then when you go in front of the focal point, then you flip to being right side up. And that's what we saw at the very beginning, this ball swinging. When you're beyond the focal point, as you are right here, when you're, let's see if I can pause it at the right time. Oops, let's maybe hit. Okay, when you're beyond the focal point, you'll see that you're upside down. See how the blue is on the bottom and the blue is on the top? But then when you're inside the focal point, I may have to just use my mouse. So when you're on the focal point, you get no image, and you can see it right here. See how that's a really huge blur? This is exactly the focal point. And when you're inside the focal point, you're right side up and you're larger. And that's exactly what you're seeing from our ray tracing right here. That when you're inside the focal point, you're right side up, upright, and you're larger. But then when you go back and this thing swings beyond the focal point, now we're beyond the focal point. Now you're upside down and you're smaller. And you can see that as you're getting closer, now you're right side upside down, you're getting bigger, 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 and then no image, and then you flip around. So using this ray tracing to predict what we're seeing. We can use this ray tracing in one more way. We can use it with convex mirrors as well. So we're going to do the exact same algorithm where ray 1 comes in, it stops at the principal plane. But this time, it's going to go away from the focus. You're going to draw a line that goes exactly away from the focal point, like that. Ray 2, same idea, where we measure above, we go down below, we make a dot, and then ray 2 goes towards the middle, and then it reflects off through our dot. So again, our reflected rays, these are the reflected rays. The reflected rays are diverging, so we're going to trace them backwards. This is where my image is. My image is smaller. My image is upright. And my image is virtual. It's virtual because I had to trace it backwards. When I trace these backwards, that makes a virtual image. Maybe we'll put it at a different place. Oops, sorry. So no matter, let's place it closer once. I mean, I know that in your notes it's got it where it was, but it doesn't make any difference with a convex mirror. You're going to hit this, go away from your focus. You're going to hit there, and you're going to bounce like that. And these reflected rays are always going to be diverging, and you're going to have to always trace them backwards to find your image. Again, it's going to be the same thing. Smaller, upright, and virtual. So, to summarize, when we have a convex mirror, it's always smaller, it's always upright, and it's always virtual. Convex mirror, pretty straightforward. Concave mirrors, it depends. If you're beyond the center, you get a smaller, upside down real image. If you're on the center, as we are here, if you're on the center, you get the same size, real inverted image. If you're in between the center and the focus, you get a bigger, my image was here, you get a bigger, upside down, and real image. And if you're on the focus, you get no image. And if you're in between the focus and the mirror itself, you get a larger, right side up, and virtual image. So ray tracing, following these steps, using a straight edge, some of the pitfalls that I see when I have students do this. Number one, the biggest pitfall that I see when I have people doing this is they don't draw the principal plane. I can tell you right now, probably 30% of you will get that wrong on the first quiz. You'll forget to draw that line, and then you'll draw the ray goes all the way to the mirror in a way, and that's wrong. Number two, people don't do dotted lines. If you ever go behind the mirror, those are dotted lines. They have to be dotted lines because a solid line represents the path that the light actually takes. It hits that mirror and bounces off. It hits this mirror and bounces off. Third mistake, people don't draw their image. You saw in one of the ones that I did earlier that I forgot to draw. Here's where the image is located. So I do it with an arrow because it's right side up. So this means that it's upright. So forgetting those things are some of the biggest pitfalls that I see when I have students making their ray tracing.